statements up there. We have atomic weights. Okay, what we have to do when you think about a water here, I like to set up a table because I've noticed that even my best students on test day, they think this is really super easy and they don't bother to write anything down. They're just pounding it into their calculator and they make mistakes. Here's the safe and slow way. I take this formula and I say, well, in that formula I have 2 hydrogens. Each hydrogen is contributing. Then I look up there and let's go at least 1.0. And that's the Cartwright arbitrary cutoff for how many decimal places I take. That, let me take you back. If we were doing number of protons, neutrons, and electrons, when we needed whole numbers back in chapter 1, I rounded to the nearest whole number. For this work in this chapter on, I almost always, I just pick up 1 decimal place. So I take it, I round it to the nearest 1 decimal place. So the hydrogen is contributing 2.0 total. I have 1 oxygen, and take a look up there at oxygen, and if we round it to the nearest 10th, take a look at that, to the nearest 10th. Steve, what's that going to be? 16, tell me more. 0.0. So the oxygen contributes 16 total. Then I've turned you into bookkeepers. You've got a column out here. All you have to do is add that together. Now, if we were still talking theoretically, the units on that would be AMU, atomic mass unit, that relative scale. But we want to get practical. So I'm going to write a sentence up here that's very similar to what I did for elements before. So this is going to be for compounds. If we express the formula weight, and that's what this is called. You sometimes hear it called molecular weight or molecular mass or formula mass. Unfortunately, there's a lot of different renditions. Formula weight is more general. It takes in any compound, whereas later you'll learn molecular weight is a little more limited, but you don't need to worry about that right now at all. So if, for a compound, we express the formula weight or mass in grams, this will be 1 mole of the compound or 6.02 times 10 to the 23rd molecules of the compound. Okay, now notice the parallel. Last time, on Thursday, I had a very similar thing that I said. Let me just read it how it was on Thursday. For elements, I said if we express the atomic weight in grams, this will be 1 mole of the element, or 6.02 times 10 to the 23rd atoms of the element. Okay, so see the parallels? So we have this. Now, I can take that, come over here, for compounds. If you have grams, we need to be able to get to moles. If we have moles, we need to be able to get to number of molecules, and back again. Let's try something. I can now come over here. Because I have this statement, I can say water is 18 grams per mole. I'm going to get away from that theoretical AMUs. Because of this statement, I know if I weigh out 18 grams, I've got 1 mole, right? Okay? What if today I don't weigh out 18 grams of water, I weigh out 36? How many moles do I have? 2. How'd you get that, Andrew?
Add the 2 was multiplied
passwords at it, but yeah, that worked. Okay, we got 36. And how do we get to the number one? Divide it, exactly. See, you did that so fast and you knew what you were doing. It didn't even surface in your brain what to do. You just knew that was right. Okay, so I got 36. Andrew divided it into packets of 18. So guess what? We come over here, we go grams to moles. We divide by the formula weight. Okay? I have 10 moles of water. How many grams do I have? I have 10 moles of water. How many grams? 180. What did we do? Brittany, what did you do to get that?
Multiplied it times 100 or times 18.
Perfect. You see how this is so parallel? Okay, and then from moles to molecules, guess what we do to go here? Multiply. This is identical. Okay? Identical. Now, let's do one more formula way to be sure everybody's up to speed on this, and then we'll start working problems like this. Let me take another compound. HNO3. That happens to be nitric acid. There used to be a really good usage of it. They no longer use it, I don't think. But if you had a wart on your hand or on your foot, you could go to a physician, and years ago there were several different things they could do to take the wart off. One, they could cut it off. Okay, so they're cutting, and then they've got to stitch it, and you got a chance for infection. Not a real good way of doing it, but not impossible. Then they also can burn them off. Well, that's not real nice, because here's your hand and they're burning something and you're smelling your own burning flesh. Not nice. Okay, they can also freeze them off, and that's usually what they do now. They freeze them off. What they did years ago is they take a metal probe, dangle it into liquid nitrogen for several minutes. Liquid nitrogen has a temperature of minus, I believe it's minus 196 degrees Celsius. I mean, we're talking cold. Then they bring out that metal probe, touch it on your skin for a minute, and that would kill the tissue, kill the virus, and it would slump off. Nitric acid is kind of interesting, is that they could also put nitric acid on it, and you would burn it off chemically. One time when I was in graduate school, we had a clinic at the university. So I had a wart in my hand, so I hike across to the clinic on the university, and he takes nitric acid, puts it on, and kills it, and it sloughs off and it's dead. Okay, so I asked the guy, I said, now did you use concentrated nitric acid? And he goes, oh yeah. I go, fine. So next time I have a wart, I'm in the lab, we have concentrated nitric. I just think, why walk across campus, do it myself. Okay, I learned real quick, the term concentrated is relative. What is concentrated to that guy was dilute to me, so I take the concentrated acid, put it on my skin, the big hurt immediately. So I run for water. So the point is, not all acids are created equal. One person's concentrated is not the same as another person's concentrated. But, to get back, I want to do the formula way. Okay, we have hydrogen, we have nitrogen, and we have oxygen in this thing. Okay, Russell, how many hydrogens? One at, what do I use for its contribution?
1.0.
1.0, so it makes 1.0. And Clint, how many nitrogens?
1.
1. And what contribution is the nitrogen making?
1.0.
Wait, that was hydrogen.
Oh.
Nitrogen, how much does it?
14.
14 to the nearest 10?
0.
1, 0. You want to keep your column out here, straight down here. Addie, how many of oxygens do I have?
3.
3, and each one is making what contribution?
16.0.
16.0, and what's that, 48? Okay, and all we have to do, this is the safe way, we just add up that last. Liz, what would you get for the formula way? 63.
0.0.
And the units are You can say AMUs, but if we want to get practical, we won't say AMU anymore. What will we say? Grams per